Welcome back to the Deep Dive. Today we are tackling what feels like the biggest mystery in modern tech, the black box of artificial intelligence.
Right.
I mean, these systems are everywhere. They influence almost every part of our lives. They're determining loan approvals, filtering job applicants even giving input on critical medical decisions.
And that influence is exactly why let's call it secrecy surrounding how they decide things is such a growing problem. I mean, when an AI system can't explain its own reasoning, it becomes impossible to audit or question or even fix.
Okay, let's unpack this.
Right.
Our mission today is to crack open that box. We are diving deep into the technical tools and frameworks that define what we call explainable AI, or XAI. We've synthesized a collection of sources that give a really student-friendly, but still technically grounded, look at how experts are achieving transparency. We'll be looking at key tools like SHAP, LIME, DALEX, PDP, and ICE.
And what's so fascinating here is how the source material connects these technical methods directly to the ethical goals of responsible AI.
Yeah.
The core mission of XAI, as all the research points out, is to make sure systems hit 4 crucial goals. Sometimes it's called TAFT. They have to be transparent so we can see the logic, accountable so they can be fully audited, fair so they're checked for bias, and ultimately trustworthy when we put them out in the real world.
To keep this conversation grounded, we're going to follow the source's main example, which is the UCI Adult Income dataset.
A classic.
It's a model that predicts whether a person earns more than $50,000 a year. It's a simple yes or no.
A binary prediction, yeah.
And it's based on features like education level, relationship status, capital gains or losses, hours worked per week, things like that. We'll use this income prediction scenario to see what each of these XAI tools actually shows us.
Sounds good.
So before we get into the alphabet soup of all the tools, we really need to clarify what we're trying to explain in the first place. The sources divide this really cleanly into 2 distinct pillars.
That's a necessary starting point. The first is what we call global explainability.
The big picture.
The big picture, exactly. The macroscopic view. It's about understanding the model's general tendencies, its overall behavior. It answers questions like, across the whole data set, which features age, education, capital gain, are the most influential overall.
Right.
And this perspective is just crucial for developers who are trying to improve the model and make sure its overall patterns make sense.
So that's the general theory of the model.
Precisely. And then on the other hand, you have local explainability. This is the individual perspective. It's hyper-focused on why one specific prediction happened.
Okay, so if I get denied a loan...
Exactly. If someone was denied a loan, local explainability tells that person how much their specific age pushed the denial probability up and, say, how much their salary pushed it down. It provides direct accountability to the user.
I see. So if global explainability helps the developer improve the machine, local explainability helps me, the individual, understand the machine's judgment of me.
You've got it. That's the core distinction.
That makes a lot of sense. Let's start with the tool that, according to our sources, really revolutionized XAI, SHAP, which stands for Shapley Additive Explanations.
SHA. It's brilliant, really, because it provides a foundation that's based on game theory, specifically something called Shapley values.
Okay, game theory. So how does that work?
Well, imagine a team of players, right? Each feature, like education or age, is a player, and they all contribute to a collective outcome, which is the final prediction. The final score. And SHAP calculates the exact fair distribution of credit or blame among those feature players for that score.
The elegance of that is the consistency, I guess.
It is. I mean, unlike some other methods, SHAP is mathematically guaranteed to ensure that the contributions of all the features, when you add them all up, they exactly equal the difference between the model's average prediction, the base rate, and the final prediction for that one person. That exact summation is why it's so powerful and so trusted.
Let's look at the 2 main ways SHAP communicates this, starting with the global view, the bar plot.
The bar plot, right. This just summarizes the average magnitude of impact. It averages the absolute contribution, whether it's positive or negative, of each feature across the entire data set.
So for our income model, the longest bars would clearly be what?
Education level, relationship status, and capital gain. Those would have the longest bars, showing they're the model's main drivers. It's a really fast way to get the importance ranking.
But where it gets really interesting, I think, and where the local insight shines, is the SHAP force plot. Right. For you listening, try to imagine a kind of a tug-of-war visualization.
Yeah, that's a great way to put it. It's centered on the model's average prediction, the base value.
The starting line.
Right. Let's take adult number 10 from the dataset. That person's specific prediction is the destination. Features colored in red are like forces pushing the prediction toward a high-income outcome, over 50K.
And blue pulls it down.
And features colored in blue are forces pulling it down toward the low-income outcome. And the length of that color bar shows the magnitude, the strength of that push or pull for that specific person.
So we might see adult number 10 has a high education level, and that shows up as a long, strong red bar.
Pushing it up.
But maybe they only work 20 hours a week, and that shows up as a strong, long blue bar, pulling it back down.
That's the accountability. It visualizes the internal logic. You can see which factors were decisive and which were, negligible for that one person.
Now, if you want the ultimate summary, combining the individual detail and the global overview, the sources point to the SHAP Bees worm plot. This is where we can really start to see complex interactions.
This one requires a bit of visual imagination, for sure. Picture the features ranked vertically by importance. Horizontally, you have the SHAP value, the impact.
0 is in the middle.
0 in the middle. Positive impact is on the right, negative is on the left.
And the plot is made up of thousands of little dots, right? Each dot is one person.
Exactly. And the color of that dot reveals the person's actual value for that feature. So dark blue might mean low education and dark red means high education.
And this is where the key insight comes from, this combination of position and color. It shows correlation and interaction.
Yes. Look at the education feature. If the model's working as you'd expect, you'll see a dense swarm of red dots clustered heavily on the right side of the plot.
The positive side.
The positive side. This tells you two things. First, high education, the red dots, consistently drives predictions up. And second, because the dots are pretty well clustered, the effect of education is generally stable.
But what if we look at a feature like, say, age, and we see the red dots, the older people, are spread all over the place, some pushing income up, some pushing it down.
That widespread signals heavy interaction. The effect of age isn't universal. It depends heavily on other features like their education or maybe their capital gain. An older person might only get a positive prediction if they also have high capital gains.
So the Beesworm plot is the test for that variability.
It's the litmus test for understanding variability and dependence. Absolutely.
Okay, so SAP is technically precise, but I imagine its calculation can be pretty demanding, especially on these huge, complex models.
Oh, yeah. That heavy computation can sometimes make it impractical for quick, high-volume local explanations.
And that brings us perfectly to our next tool, LIME.
Yeah.
Local Interpretable Model Agnostic Explanation.
It's the one.
So why do we need LIME if we already have the precision of SHAP?
Speed and model agnosticism. LIME is designed for speed. It doesn't rely on that complex mathematical foundation of Shapley values. Instead, LIME explains one prediction at a time using this clever approximation trick.
Okay, walk us through that approximation using our adult number 10 again.
So LIME basically asks, how does this person's prediction change if we just slightly alter their details? It creates thousands of fictional neighbors around adult number 10 by tweaking features like their age or hours worked.
And then it runs those neighbors through the original black box.
Exactly. It asks the complex model to predict for all those neighbors. And based on those predictions, LIME then creates a simple, weighted linear model, a highly interpretable stand-in that accurately mirrors the complex model's behavior, but only in that immediate area.
So it's a local map.
It's just a local map. And that simple model gives you the feature contributions very, very quickly.
So it's a trade-off. We gain speed and flexibility because LIME works on any black box model.
Anything at all.
But we lose the mathematical exactness that SHAP guarantees.
That is the key difference. The sources show that for adult number 10, both SHAP and LIME will generally agree on the direction. Education is positive, relationship is negative. But LIME's approximation might sometimes miss the true magnitude if the complex model has some sharp, nonlinear behavior right near that person.
And for even quicker, more human-friendly summaries, especially for simpler models, the sources bring up ELI 5.
ELI 5. Explain like I'm 5, which, lives up to its name. It's all about simplicity and readability. It's great at taking contributions from models that are already pretty interpretable, like decision trees or linear regression, and just boiling them down into these clear text-based summaries. Feature X contributed 15 points toward the positive class.
It sounds like a great first pass tool. Like use ELI 5 for a quick overview or to explain a decision tree, but then you turn to SHA for the deep fundamental mechanism of a neural network.
That's the strategic use, exactly. ELI 5 gives you the quick what, SHA gives you the detailed how and why.
Okay, so now we can shift gears a bit from simply explaining decisions to actively auditing the model. For diagnostics, for fairness, this is crucial in high-stakes environments.
It is.
And this brings us to what the sources frame as a serious accountability framework. DALEX descriptive machine learning explanations.
Yeah, DALEX really positions itself as a comprehensive auditing framework. Its tools are designed not just to show what features matter, but to rigorously check the model's performance and consistency across different groups of people. It's ideal for regulatory checks.
How does DALEX figure out feature importance differently from SA? We saw SA uses contribution magnitude.
DALEX uses a method that's tied directly to the model's performance. It's often called permutation importance.
Okay.
So instead of calculating a feature's theoretical contribution, DALEX measures its dependency. It takes the training data and it deliberately shuffles or scrambles up all the values for one single feature, let's say education, and then it measures how much the model's accuracy drops on that scrambled data.
So if the model's accuracy just tanks when education is scrambled, that means education was essential.
Absolutely essential. The bigger the performance drop, the more important that feature is to the model's predictive power. It's a very robust check of feature necessity.
And moving to diagnostics, DALEX and other frameworks rely on two really powerful visualizations, PDP and ICE. Let's start with the average trend, the partial dependence plot, or PDP.
Right. PDP tells you the average story for the model. It asks a simple question. If we change this one feature, say hours worked, from 10 to 60, how does the model's average prediction change across the whole dataset, holding everything else constant?
So for the inquiry model, the PDP for education would show a clear upward curve,
You'd hope so.
a higher probability of high income as education increases. And the sources also mention that for hours worked per week, the curve rises up to about 40 hours, and then it just plateaus.
Which makes perfect sense. It visually confirms the model has learned the idea of diminishing returns after a typical full-time work week.
But that curve is just the average of everyone. The real power for auditing comes when we look at ICE.
Individual conditional expectation, yes.
And I understand that the PDP line is actually just the mean of all the ICE lines.
That's the precise relationship. ICE plots show the individual stories. Instead of one average line, you see thousands of thin gray lines. Each of those lines shows how one single person's prediction changes as that one feature is varied.
This sounds like the crucial diagnostic step. Because if those thousands of gray ICE lines all kind of follow the main blue PDP line, that signals consistency.
Right. The model is treating everyone more or less the same based on that feature.
But if the ICD lines go wild, if they diverge or crisscross,
That is a massive red flag. It signals strong model interactions or potentially seriously inconsistent treatment based on some other hidden correlated factor.
and this capability is what makes ICE so powerful for finding potential bias, isn't it?
It's exactly that. It allows us to compare feature trends based on sensitive attributes, things that might have even been excluded from the model directly.
The source material gives a pretty stark example here, comparing the ICE curves for men and women on the education feature.
A really important one.
Walk us through what that visual revelation looks like.
Okay, so if the model were perfectly equitable, the thick blue PDP line representing the average prediction for women would basically track the PDP line for men as education increases. They'd be on top of each other.
But that's not what they found.
No. The sources found that when you factor in sex for the analysis, the blue PDP line for women was consistently lower and even flatter than the line for males at the same education levels.
Wow. So that immediately reveals a learned pattern of disparity.
It's right there in front of you. The model, just based on the historical data it trained on, has learned to assign a lower probability of high income to women compared to men, even when their education level is identical.
It's a direct visualization of the model's internal logic, treating different groups unevenly. So ICE doesn't just explain a prediction. It shines a light on the underlying assumptions, the biases that the model has learned from the data.
And that is just essential knowledge for accountability.
This has been a complete tour of the XAI toolkit, from, precise quantification to crucial auditing. Let's just quickly solidify the strategic utility of these tools for everyone listening.
Okay. If your need is deep theory-backed understanding and you require the exact contribution of every feature, you have to use SHAP. The mathematical guarantee is your baseline for trust.
Right. But if your goal is diagnostics, auditing for fairness, looking for that inconsistent treatment.
Then you build your stack using DALEX for the performance checks, and you use those paired visualizations of PDP and ICE.
And finally, when you just need a quick model-agnostic local approximation, maybe the model is just too big or slow for SHAP.
Lime. Lime provides that speedy, local stand-in explanation. It's your go-to for a fast answer.
This material really shows us that explainability. It isn't just a technical footnote, is it? It's the absolute foundation for building AI systems that are safe, ethical, and, trustworthy in society.
I mean, we've spent this time opening the black box, and with tools like ICE, we've seen how we can diagnose where a model has learned potentially biased patterns from historical data, like that income disparity. So the question we want to leave you with, and it's what the whole field is grappling with, is this. Now that XAI gives us a clear diagnosis of the model's illness, what specific technical structures, data interventions, or ethical guidelines do we need to actually prescribe the cure and actively mitigate that unfairness before the system gets deployed?